My name is Sam Caldwell, and welcome to my capstone presentation about the contraction mapping theorem. So the contraction mapping theorem is one of the more useful tools that we have for finding some not so easy to find solutions to nonlinear functions. And in general, the theorem just states that if you have a contraction mapping on a complete metric space, you can construct a sequence of iterates in order to find some fixed point in this set. And depending on how you define your sequence on your function, you can use this to find any sort of a point in your set that you want. Contraction mappings allow us to do this as they simply map points on sets closer to each other, right? So that's what they call contraction mappings. And then this property allows us to find some unique fixed point in this set through some algebraic manipulation and some clever calculations. So the first thing we'll do is we'll begin by establishing some definitions relevant to metric spaces and what we mean by completeness as it pertains to metric spaces. And then we'll move into formally defining contraction mappings and then proving the contraction mapping theorem through a series of steps. And finally, we'll talk a little bit about the role of contraction mappings in fixed point iterative sequences, in particular Newton's method. We won't talk as much about this, but if you want to read more about the results that I find, it'll be in my paper. So first, we want to define what a metric space is, right? So if you have a set M and some distance function where you take 2 points in M and map it to R, this is a metric on M if for all x and y in M, right? The distance between these 2 points is greater than or equal to 0, with the distance being 0 if and only if these points are the same point, right? And then the distance between x and y is equal to the distance between y and x, so the ordering doesn't necessarily matter for the distance function. And then for all z and m, we have the triangle inequality, right? So the distance between x and y is less than or equal to the distance between x and z plus the distance between z and y. So these three properties shouldn't be unfamiliar. And let's define what we mean by convergence in metric spaces, right? So if you have a sequence in a metric space, we say the sequence converges to an element in your set if for all epsilon greater than 0, there exists some natural number such that the distance between x sub n, right, your iterate, and x is less than epsilon when little n is greater than or equal to your natural number, capital N. And then similar to how you would work with the reals when you establish convergence, you can write this in terms of limits. So the limit as n approaches infinity of x sub n is equal to x. And now let's define continuity. So if you have two metric spaces, x with d1 and y with d2, note these are two different metrics. If you have a function that maps x onto y, this function is continuous at some point x in x. If for all epsilon greater than 0, there exists a delta greater than 0 such that the second distance function between the images of x and y under f is less than epsilon whenever the distance between x and y is less than delta for the first distance function, right? So these definitions aren't necessarily foreign to those who have studied real analysis before, but these simply extend those concepts up into metric spaces in general, right? And so as far as continuity goes, you have to be more specific about what your metrics are, because between your spaces, they might not necessarily be the same. But as far as the reals go, it should be the same. So now let's get into Cauchy sequences. So again, suppose you have a metric space and a sequence in this metric space. We say this sequence is Cauchy if for all epsilon greater than 0, there exists some natural number n such that the distance between x sub n and x sub n is less than epsilon whenever m and n are greater than or equal to n, right? So past this natural number n iterates out from your sequence, right? These 2 points become arbitrarily close together. And like I said, these definitions are really no different than those taught in undergraduate real analysis courses, but we need to make the distinction that this is for metric spaces in general, rather than just Rn spaces, or rather specific n-dimensional Euclidean spaces. Because again, you might not necessarily know that the metrics or the sets would be the same. And so whenever we're talking about Cauchy sequences, it's important to remember this, because we'll sort of base our definition of completeness for metric spaces on this concept, right? So we say that a metric space is complete if and only if every Cauchy sequence in this space converges to a point in your set N, right? And so in R, this condition is equivalent to the axiom of completeness, and this holds true for higher dimensional Rn spaces with their standard metrics as well. However, like I said, depending on your metric, this will certainly not hold true for every space. So, as an example of this, so to sort of demonstrate how this works, if you have some set x and a distance function, right, a metric given by this here, we say that, or we see that for this sequence here, 1 plus 1 over n, all that raised to the n for n, an element of the natural numbers. We can see that this sequence here is a Cauchy sequence, right, as n goes off into infinity. I only graph this up to n equals 50. But we can see that as we increase our number of iterates here, the iterates become arbitrarily closer to each other, right? So it satisfies our definition of Cauchy. So now let's suppose our set X is the set of reals, right? So we could see from this dotted line here that I put at E that we could say that this sequence here converges to E. Right? We're getting closer and closer to E. However, let's suppose our set X is the rationals, right? So this Cauchy sequence here is in fact a Cauchy sequence of rationals. However, we cannot say that this sequence converges to E, since E is irrational. Therefore, this is a Cauchy sequence which does not converge, and so we could say that the metric space of the rationals with this particular distance function is not complete. So now let's move on to a formal definition of contraction mappings. So again, suppose you have a complete metric space. Notice that we're restricting ourselves now to complete metric spaces. And let T that maps end onto itself be a mapping. We say that T is a contraction mapping if the distance between the images of x and y for arbitrary elements of n, x and y, under T is less than or equal to the distance between x and y times some constant k, where k is fixed and it's strictly between 0 and 1. We call k our contraction constant or our Lipschitz constant. And then real quick, let's discuss what a fixed point is. A fixed point is just simply a point in your set where under this mapping t of x is equal to x, so it maps to itself. So quickly, let's go through a quick proof of that every contraction mapping is continuous. So again, suppose we have a complete metric space with some contraction mapping t and Lipschitz constant k, and then let's let x and y just be arbitrary elements of n. Now let's walk through this like a normal continuity proof. Let's let epsilon be greater than 0, and let's suppose that delta is equal to epsilon. Now, if the distance between x and y is less than delta, then this implies, by our definition of contraction mapping, that the distance between t of x and t of y is less than or equal to the distance between x and y times our contraction constant k. Now, since we have that our distance between x and y is strictly less than delta, we can turn this into k times delta, and since k is strictly between 0 and 1, and delta is equal to epsilon, we have that k times delta is strictly less than epsilon. So we have proven that contraction mappings are in fact continuous at this point x, and then since x is really just any point in your set, and we have that t is continuous on your set now. So now we can start walking through our proof of the contraction mapping theorem. So formally, the theorem just says, again, suppose you have a complete metric space and a contraction mapping with Lipschitz constant k, and T has a unique fixed point in your set. Let's say this fixed point is x. Furthermore, if y1 is just some arbitrary element of your set M, then the iterates given by this sequence where x0 is equal to y1, x1 is equal to t of y1, x2 is equal to t of y1, so on until you get to x sub n. This has the property that this sequence will converge to your fixed point x. So let's walk through this proof through 3 steps. The first thing we'll do is construct a sequence using our contraction mapping and prove that it is in fact Cauchy. And then we'll take a point at which our Cauchy sequence converges and show that this value is our fixed point and that it is unique. And then finally, we'll show that if we have if we let any arbitrary point in our set be our initial value, then our sequence will also converge to your fixed point. So let's consider, complete metric space contraction mapping with constant k. And let's consider the sequence of the form discussed earlier. y1, t of y1, t of t y1, so on and so forth. So let's show that this sequence is Cauchy. So by the triangle inequality, we have the following relationship between really any 2 points in our sequence, xn and xn, such that m is less than or equal to n, right? So the distance between x sub m and x sub n is less than or equal to this here. And since we know that T is a contraction mapping, we also have that for any arbitrary element of our sequence. Let's just say x sub a. The following is true, that the distance between x sub a and then its successor x sub a plus 1, this is equal to the distance between images of x sub a minus 1 and x sub a, which is less than or equal to k times the distance between x sub a minus 1 and x sub a. And so similarly, you can write this down for every other element of our, or iterate of our sequence all the way down until x sub 1 and x sub 2. Which implies that for the distance between any random iterate, x sub a and x sub a plus 1, this is less than or equal to k raised to the a times the distance between x0 and x1, right? You can stack these k's as you work your way down this inequality. And then since we know that k is strictly between 0 and 1, we can see that this sequence does indeed converge. But let's walk through the formal epsilon proof that this is the case. So then combining these insights, we get this here, that the distance between x sub m and x sub n is less than or equal to k raised to the m plus k raised to the n plus 1, so on until you get to k raised to the n minus 1 times the distance between x0 and x1. And so from here you can factor out k raised to the m, and then you can rewrite this inequality as such. And so really 1 plus k squared plus so on is really just a finite partial sum of the series representation of 1 over 1 minus k. So you can substitute that in and make this a strict inequality, and you get this particular inequality right here. So this gives us an idea of how we want our epsilon to interact with our inequality here. So we can begin our proof. Now suppose epsilon is greater than 0. And then since k is less than 1, we have that kn approaches 0 as n goes off into infinity. Therefore, there exists some natural number n such that k raised to the n is less than epsilon times 1 over k times 1 minus k times 1 over the distance between x0 and x1. And if capital N, our natural number, is less than or equal to n, which is less than or equal to n, and this implies that our distance between xn and xn is less than epsilon, which is what we want, right? So if you move every term over here, leaving epsilon on the right, we essentially get that this distance here is less than epsilon. Therefore, we've shown that this sequence is in fact Cauchy. And since our space is complete, we can say that this sequence must converge to some point in your set. So let's just say that the limit of x sub n as n approaches infinity is equal to x. And so we want to show that this limit, or x, is a fixed point of our function. And then, so since our contraction mapping is necessarily continuous, as we've shown, we know that if the sequence x sub n approaches x as n goes off into infinity, then the limit as n approaches infinity of t of x sub n is equal to t of x. So let's consider this limit here. X sub n is equal to x as n goes into infinity. Now, since we have that t of x sub n minus 1 is equal to x sub n, we can plug that in. And now again, since our function is continuous, we can pull this limit inside our function. And since the limit of x sub n as n goes into infinity is equal to the limit of x sub n minus 1 as n goes to infinity, which is equal to x, we can plug that in, and we have obtained that x is in fact a fixed point of our contraction mapping, right? And so now we have to show that this fixed point is unique. And this is pretty simple. We can do this by contradiction, and we can simply assume that our function has two fixed points. Let's just say x and y. So let's consider the distance between these 2 points. And from our definition of the contraction mapping, we have that the distance between x and y is less than or equal to k times the distance between x and y. But since k cannot be 1 strictly between 0 and 1, this inequality cannot occur. So it must be that actually x and y are the same point. So therefore, t has a unique fixed point. Now our final step follows pretty easily from our previous results. So the fact that if we use an arbitrary point in our set for an initial value, our sequence will converge to the fixed point. We can simply suppose that a new sequence converges to a different point, say x prime. It must be that this point is also a fixed point of t by our second result. And then since our fixed point must also be unique, we have that x is equal to x prime. And so really we are done with our proof of the contraction mapping theorem. So why is the contraction mapping theorem important, right? Where can it be useful? And I sort of mentioned that the contraction mapping theorem is used extensively in fixed point iterative sequences, of which Newton's method is a part of, right? So Newton's method is just a root finding method for functions. In particular, it's useful for nonlinear functions. And all it does is it uses this following sequence of iterates for some twice differentiable function g of x, right? And under the right circumstances, this function here is a contraction mapping, and therefore we can construct a sequence of iterates that will converge to the root of a function of interest, right? So based on how we've defined our function, and based on what function we're basing also off of, basing this function off of our fixed point should be a root of our function of interest. But like I mentioned earlier, if this is not your function, or rather if this is a different function and you define your sequence of iterates differently, you can really have your fixed point be any set, or any point in your set. So here's the formal result proving that Newton's method acts in this way. I'm not going to walk through the proof of this, as there are some results that we don't quite have time to discuss here. But if you'd like to read more into the proofs and sort of some of the motivations behind why this works, it'll be in my paper. So if g is just some twice continuously differentiable function on some closed and bounded interval of the reals, let's call it I, such that g of a is less than 0 and g of b is greater than 0, right? So there's change of signs here, such that 0 is less than the absolute value of g prime of x, which is less than or equal to k, which is at less than 1, for all x in your interval, and k between 0 and 1, right? So k is our contraction mapping constant here, or Lipschitz constant. Then there is some alpha in your interval I such that g of alpha is equal to 0, right? So that's our fixed point. And furthermore, this function given by Newton's method is a contraction mapping, and we can construct a sequence of iterates that will converge to your fixed point, which is your root. So let's just walk through a quick example here without getting into the nitty-gritty details of why this works. Newton's method, you simply have to find a local neighborhood around which a root of a function exists, and then you simply find our initial value and then run it through Newton's method. So let's just find the first 6 iterations. the positive root of this polynomial given here. F of x is equal to x to the sixth minus x to the fifth minus 2. And this particular positive root isn't very pretty. There is a negative root that is 2, but that's not particularly interesting. So we can see here by plugging in values that there is a root between 1 and 2. So let's start with a y1 of 1.1, right? Let's have that be our initial value. You plug that in, and then by the sixth iterate, you can see that we get 1.38809. 4605, and that is actually accurate up to the fifth decimal place. So after 6 iterations, 5 decimal places is rather good. And I sort of talk more about the accuracy of fixed point iterative methods under the contraction mapping theorem 1 in my paper. So if you'd like to read more about that, it's there for you. Now, the contraction mapping theorem is really much more important than described here. This is some rather basic information when it comes to contraction mappings. And really its utility comes from its generality, right? So my particular example about Newton's method really kind of narrows down on closed pattern intervals on the reals. However, like I said, contraction mappings and complete metric spaces aren't necessarily restricted to Rn spaces, right? So the contraction mapping theorem is used extensively in functional analysis on Banach spaces or normed vector spaces. And it's frequently used to find the existence and uniqueness of initial value problems and their solutions for partial differential equations, right? And depending on your space, this can get incredibly complicated, but the contraction mapping theorem is a very useful tool for that purpose. And some of my sources go more into detail on that if you would like to read more about that. And so really, that's all I have. I want to thank my advisor, Dr. Garth, and my professor, Dr. Ryan, and thank you for all my fellow Capstone classmates' opinions and help on this paper. So, alrighty, thank you very much.